Hey, John here. So I ordered this on eBay the other day. Somebody on my channel sent a message that said, hey, have you heard of this thing? Maybe it's of interest. I looked at it. I read some stuff about it. I've never heard of this company before. I'm not from Ottawa, Canada. What this is it's a personal computer that is designed to be connected to a cable company set-top box in the home. The idea was you could buy this, which I can't imagine was cheap by any definition of the word, plug it into your set-top box, you'd have a home computer, and the cable company would have provided, file access and stuff like that. Now, you might not think much of this today when the internet's in everyone's home, but this was before anyone really knew what the internet was, certainly not the common person. So, what we're going to find in here, if I understand correctly, is a cable set-top box with a Z80 in it that actually works a whole lot like the Retro board that I've been tinkering with on my series, the same name. There we go. And what I'm hoping I can do with this is just, in theory, replace the boot ROM and boot up CPM and stuff like that on it. According to their marketing materials, the machine here did and was capable of running CPM when it was connected to the cable system. And the idea was, it would boot up and download its operating system through the cable system. So let's see what's in all these boxes here. This is bigger than my camera is shooting here. So this is the PM Link Plus. Okay, so somebody, this Pell Mill is the name of the guy selling these things on the internet, and they're selling, cable or internet streaming video services and stuff like that. And if you look at the listing, this thing is marked as, a complete computer, but you need to have your own EEPROM and stuff. The idea is, you probably can't do much with this unless it's 1985 and you're in Ottawa and you've got whatever NABU cable company. It comes with a little piece of cable connector and a funky DIN connector that you can use to plug this into their cable system, which I'm sure no longer exists. Wow, here's your personal computer's guide. That's great. All right, so what do we got here? Keyboard. I'm assuming this thing will actually run. If I were to power it up, and we'll find out in a few minutes. Oh, TV, NABU. NABU, who knows how to say this thing? Somebody tell me. Go, delete. Wow, that's great. So you've got two Atari, I'm sure, compatible joystick connectors. That's what they would have looked like. And this is another DIN connector that you use to connect the keyboard up to the main computer. Wow. Revision whatever. Part number blah. Keyboard unit. Serial number 860. Yeah, I don't know. There's like a date code on the end of this box that says 1984 somewhere when I was poking around on here. Yeah, one of the ends of this box here. Let's see if I can find it. Yeah, right here. Here's my serial number, 8650, and I don't know, is that, yeah. 10/2/1984 was when this was manufactured. And you can find some YouTube clips about, there's a university somewhere trying to reconstruct the old, a small cable system so these things will run or whatever. And there's a little write-up on it in there. But I am interested in seeing if I can use this pretty much as is with a minimum of hacking. I mean, if I do, when I post the code, you can just redo your own flash, and there you've got a whole PC. And I'm a CPM guy, so if I can get CPM to boot on there and I share it with boot ROMs and stuff, hey, you're done. And you got yourself a whole system for like $59 or whatever this thing is. And obviously brand new, still in the box here. far as I can tell, I'm the only fingerprints on here, and this would show. Even if I do this right now, you'd see that, you know, the grease causes this kind of metal to get weird rust marks on it. So what do we got here? We got a regular North American Edison style outlet. What do they call it? An L20, whatever. Standard outlet for at least where I'm from in the US. You've got, you know, a power button, a reset button on here. These are a couple of LEDs on here. When I first saw the photo of this on eBay, I thought this might be a, you know, a floppy drive or something, which would be super cool, but no. So this thing is kind of landlocked, and by that I mean this is all you got: a keyboard. You can hook up what appears to be a Centronic style printer. Obviously, we need to make a cable adapter for that, and this plugs into your cable set-top box. The video and audio comes out here. It also comes out through this connector here, modulated to be watched on TV, North America, NTSC style TV on channel 3 or 4. So, how do we open it up? I don't even care about powering it up. We need to open this sucker. Let's see what's inside there. Okay. So, here we go. I'll probably hit the camera with my screwdriver here. All right, take out a couple of these screws. I love that they always put bags on these cords, you know. Like, you know, I guess some people would get upset that, ooh, I'm more upset that the rubber band that used to be in here disintegrated. It's like a rock hard. It's not even gooey. It's gone to solid. Anyway, they bag these things as if, you know, it's like this thing is going to be a problem. I don't know why that. Oh, you know why they do that? It just dawned on me. The styrofoam in there will react against this PVC and slowly melt. That must be why they do this. Because I'm like, why do they put these bags in there? Never thought about that. You know why I know that's true? Because a while ago, I opened up my old VIC-20 and the cord melted all the styrofoam in the box. And now it's a mess. So I guess I'm glad they did that. Not so happy with the rubber band, but at least it didn't get welded into the styrofoam. Alrighty, here we go. Mr. NABU. Mr. NABU. All right, so this is 25 years old. New old stock, right? So we can see these capacitors here already never probably even been powered on since it was tested. These we should give it a close eyeball on with a magnifying glass to see if they've leaked. There's an aerial resistor here. It's a little bent. I don't know what that's all about. We'll have to figure that out. It's obviously part of the video output circuitry over here. This is a TMS9918. So one of the interests I had on this is the fact that it uses the the related chip to the one that I chose that I wanted to play with on my Z80 Retro project. So if I'm lucky, the code for the Retro board may work with this as well. So it has a little EEPROM over here. Here's the Z80. This has got a Z80, must be a Z80A, because it runs at like 3.8 megahertz. Gee, I wonder where that clock comes from, right? It runs at the clock speed that is spit out by the same crystal that runs this, which is right here. Oops, a little out of camera view there, which is the color burst crystal right there. So you can already see this without even looking at the schematic that they put in the little adjustable crystal that we saw in the Z80 Retro series as one of the load capacitors, which is the schematic right out of the Steve CRC article, that I showed earlier. You don't want to beat around too much with a screwdriver. You break the components or something, right? So this guy, we'll look at the schematic eventually, but they used a coil as part of the filter for the power for their video output circuitry, which is one of the many options I chose to put in my retro video card. So this is actually not far from where I'm at, but they also did one more thing that I didn't think of, and we'll look at that as time goes on, as we tinker around with this and try and figure out how the whole thing works, if we can boot it up. So yeah, there's already, in my opinion, it's already paid itself off to confirm that we can use probably the video circuitry that I cobbled together from various other designs already as a bit of a confirm here, right? Because, you know, they probably put a little more effort into designing and testing this than I did in my first draft of my board design. Okay, so I'm encouraged by this. I'm not encouraged by me not putting in an adjustable capacitor on mine. Makes me wonder if that's going to be necessary. And the other thing that makes me wonder is that the color that comes out of my test rig on the breadboard in my design, it's a little off. The reds are not they're a little more orangey or browny, and the yellows are too. So it makes me wonder if this needs to be adjusted on my design. Of course, it may be fine once I put it on a board, because there's so much stray parasitic capacitance on a breadboard that I have no idea what mine will look like when I put it on an actual board, is my point, right? So all these funky things around here that are sticking up in the air, these got to be bypass capacitors. I don't know what those are. They look like giant glass blocks. I don't know how easily that is to see there. So what the heck kind of capacitors are these? I mean, obviously they're bypass caps, but I've never seen them in these big plastic rectangular things on there. I don't know. It's kind of weird. Okay, it's a thing. Now, I'm assuming that if I turn this on and I plug in a composite video monitor and back here where it says video, and I plug in the keyboard, that it'll probably run some sort of a diagnostics and say, hello, I'm here, which would be very nice. I don't know. Let's try it out. I mean, I don't see any, you know, loose solder balls in here or anything like that. I don't see any capacitor leaking or anything like that. I think we're going to be okay. So before I plug it in and turn it on, I'm going to at least put the lid back on, set it down on here, because if one of these capacitors blows, it's a little annoying when that happens. It's like a party popper going off with a little more oomph than a party popper, and it'll blow all kinds of insulating, it looks like confetti blows out of this thing. And you don't want to get an eye full of that. That would just be annoying. So I guess they give you this massive long cable, because this would have gone on your TV and this would have run the keyboard back to your couch or something where you would lounge while hacking, right? All right, so this thing here is my composite video to USB adapter. I can plug this into my PC. This is how I've been doing the screen captures from the VDP on breadboard experiments I've been doing. So let's go ahead and plug in the video. I don't know if the audio is worth anything, and I don't know if my video capture thingy screen software that I use for this will play the video, but we'll go ahead and do it anyway. We'll see if anything comes out a speaker or something. And we'll plug in the keyboard. At some point, it probably would be interesting to open this keyboard, because according to the documentation, it has like a 6801 CPU. It's got a whole microcomputer inside the keyboard just to run the keyboard and scan the joystick controller inputs and stuff like that, and to send data to this box, as we'll see at some point down the road in the schematic that this is actually a serial device. It's just a serial keyboard, standalone, powers up, and every time you hit buttons and stuff, it just simply sends character codes out. It's a write-only connection from the keyboard to this box. The box cannot control the keyboard in any way. So that gives me hope that, for example, the keyboard doesn't have to have some special data sent down to it to initialize it, which I would not know if I don't have all the detailed doc, which I only have some of the doc here. And I'm not really in the mood of decoding all the software that's in the boot ROM inside of this thing that you saw earlier. I'd like to be able to kind of do this without even looking at that, if I can get away with it, right? Now, this thing is pretty big to have on this part of my bench over here. This is normally where I record hand-drawn diagrams and stuff. I'm not sure if I can move my boom up any further away to get a bigger view of this. I don't think I really need a bigger view. Here's the machine. Why don't we stand it up like this? Because I don't want to break the connectors off and back. That's why. I'll hold it up after we boot it up, because then you'll be able to see all the LEDs here. Let me plug it in. All right, so let's see what happens here. Not too bad, no explosion. I got a bunch of LEDs that come on. It's making noise. Is there a fan in there? Oh, it went on, it said pause. This one, so it says on, pause, alert, check, reset. I guess that'll reboot it. There we go. All the LEDs just came back on. Alert went off, pause went off, check. Pause is back on. I assume it's trying to call home, ET phone home, the cable company. All right, it's okay. Let's see what happened on the screen. I think a better way to do this might be to use FF Play on the raw video device, which I believe is video 1 on this particular machine. Or not. Maybe it's video 0. That's a little bit better. So there we go. There it is. Now that's actually me booting it up the first time. Let me hit the reset button. I don't know what this thing actually does. This is after it's been sitting here a while and it says the adapter has failed. The color looks awful. My breadboard looks better than that. So maybe maybe this is a feature of that class of video adapter. So I just hit reset. Let's see what it does. NABU, it's booting up. It's initializing the video memory in there. And this is just awesome mid-80s. Look at the way that blocky, ugly font is. That is the hallmark of the 80s right there. Now this is a weird color that I wasn't even able to get to come out of my TI-9118. So it makes me wonder if we want to play with that little capacitor in there. But it does boot. It says adapter failure. I glance over at the box and the alert LED does come back on at this time. So this is not any shock at all, because this is, like I said, it's really designed to be connected up to a cable company, and it's not connected right now. And the adapter is the word that they use to describe another box that you can buy if you want, that is the box that connects up to the cable itself. So this is looking for the what you and I would call a set-top box, if you have that kind of cable service in your home today. So this is actually very encouraging. This is not a surprise at all. Now, it'd be nice if I hit the keys here, if it would do something to indicate that the keyboard is running, which it does not. So I have no idea if that's working. And that leaves us with, okay, now what? Well, here's what. All right, so the viewer on my channel that pointed me out to this product said that he ordered one from somebody on eBay, and of course I had to order one too. He can't be the only one having fun here. And he called up or contacted the seller, who is this Pell Mill guy or whatever, and the card you saw in the box. And he asked him, "Is there a schematic? Is there any other documentation?" And he's sure, and he sent this over. So this is a manual. You can actually find other manuals online, by the way, but this particular one is a little more interesting than the ones that I found Googling around. Okay, so this was put together by a guy named Greg Starks. This is the guy that posted a note to one of my videos and said, "Has anybody seen this?" And, one thing led to another, and now I own another computer. Okay, thank you, Greg, you jerk. Okay, so he's got what? He's copyright Pell Mill from here. Knock yourself out. Sent to me directly by James. Blah blah blah. Separate image files. So Greg took a bunch of individual, like JPEGs or whatever, and made them into one big PDF. So that's where this thing came from. Notes from the NABU webpage. Bunch of comments in here. The beauty of this manual, though, is that this manual talks about the software that's in the EEPROM on this chip and how it boots and how you can write your own applications and what you're supposed to do, that kind of stuff. It also includes the schematics of the motherboard inside this system. So I don't have to take all the parts out and figure it out from the traces on the circuit board. Yeah, that'd be fun, but it would take an enormous amount of time and a risk, of course, breaking it. At this point, since we have all this information, I think it would be really cool to see if we can get this thing to boot up and run like some custom code with a minimum number of modifications. So a whole new set of goals. Instead of maximizing the hacking, how little can we do to get this thing to come alive, right? Well, from this manual, we can see that it is a 4K ROM. You can replace it with an 8K, and you'll see there's a jumper in there to select the size of the ROM if we want to do that. When this thing boots up and runs, this ROM can be as it says, selected or deselected under software control. This thing boots up and does exactly the same thing as the Z80 Retro project does, except you have the one extra feature that if you want to, you can take the ROM and turn it back on again after you have shut it off. So this one, unlike the Retro, I can bring the ROM back if I want to. Now, it turns out on this particular machine that okay, great. If you really want to do it, knock yourself out. It's only 8K, so it'd be tough to fit in a whole. You could fit CPM in there, but I doubt we can fit a whole BIOS in there. And certainly you can't put any files or create, a file system or anything like that in here with apps to program and run with, right? So 8K is a little tight, is my point. So I think, off the top of my head, if we were to put a new ROM in there, it'd be nice to put some code in there that somehow was able to allow this to boot and load software off of some other device. And as we'll see in the drawings and the schematic, there are no disk drives, there are no peripherals on this thing. So that kind of is a difficult thing. It was specifically made to download code off of a cable TV link, which I'm not all that excited about reverse engineering in its entirety either. So what do we got? 64K of RAM. Talk a little bit about the address decoder. It's got a TMS9918, which is related to the 9118. It's the predecessor of the 9118. So it's the one rev older than what I'm playing around with from my retro board. And it talks, you can put it in the RF modulator in channel 3, blah, blah, blah. This one is an audio processor, the AY38910. So we can actually make genuine retro game sounds. This is definitely the audio processor that was in a lot of early video games, home games, a lot of arcade games and stuff use this sound generator, which is, that's going to be fun, the kind of cool thing to play with. And it talks a little about, you can turn on and off the RF and how that works. When you power it down, it automatically puts it back on the TV pass through, blah, blah, blah. Keyboard interface. It's got an 8251, which is a pretty primitive UART that it uses to talk to the keyboard. Printer interface is basically, it's going to be a Centronics if you break it out. Yeah, Centronics parallel. The HCCA is the thing that it, I believe this is the name that it uses for the interface that goes to the cable box, and it will run at 111 kbits per second. The Retro runs even faster when it's talking to the SD card. Now, this unfortunately is EIA RS422 instead of like RS232, but it's still asynchronous, I believe. So if we got an RS422 adapter instead of a 232, we might be able to just get, you could get like an FTDI thing, which a lot of people call that. There's other ways to do it. A CH340, a Prolific. There's all kinds of serial adapters, some of which are 422. I actually made some of these myself some time ago, so maybe it'll be fun for me to test out one of my own designs to see if I can make it go. The weird thing, though, is it runs at 111 kbits per second, and you'll see why that is in a minute. And that's a weirdo speed, incompatible with any standard speed that I've ever heard of, and probably not going to work if you just shove it into one of those FTDI things because they support standard speeds. We may have to do some custom code on a Pico or something, or an Arduino to run at this speed if we want to use this interface to squawk at the box. And this, honestly, this might be the easiest way to do this and be able to work with, you're going to have to replace, most likely, the EEPROM in there with some new code that talks a protocol that we know of. Unless you really want to go in there and reverse engineer, maybe it wouldn't be the worst thing. It's only 4K, the EEPROM that's in here. If we dump out that EEPROM and reverse, disassemble the whole thing, we could probably see what it sends out there and what it expects to come back. There must be some trivial little commands that it uses to say, please send me, a byte stream of some size to copy into RAM, and then I'll execute it. Kind of a command. I mean, it's only 4K. Now, 4K you can do a lot in, right? The early TRS-80 said 4K basic. All right? That was like, wow. And then, the advanced 8K version, right? So, I mean, you can do a fair amount of damage in 4K, but it's finite, and it's not undoable if you really want some punishment. You go in there and reverse engineer the whole thing. Okay, option card interface. Now this gives me a little more excitement. If you look inside there, in fact, even in this manual, let me see if I can find the picture. They got a picture of the innards, and there's your schematic. Gives me more hope. If you look inside here, you see these 4 white dinguses on here. I've seen photos of these things plugged in, floating around the internet if you Google for it. They use like these flat ribbon cables on here to go from here to a circuit board that sets in these little holes here, and you can see more holes up here, and the card then reaches over to the back of the box, and you can see a little plate here that's bolted on. So they do have this idea you can put cards in here, and they're going to have connectors that stick out the back if you want to. And I think they have like a floppy disk adapter and stuff like that in here. So that's what they're talking about here, and when you look at the schematic later on, you'll see that each one of the slots has some signals going to it, like a card select line, and those are coming out of a decoder, which I'm sure is another one of the, just like this is basically the Retro with older school dynamic RAM chips, a few extra parts because they could not buy a single giant RAM and a single giant flash ROM like I did. They had to do a little more glue logic and things like that to control all the chips, as you saw. The chip count is not too great in there, but they're dealing with smaller amounts of memory on the chips, and they do have other peripherals. They've got two serial interfaces, one for the HCCA, another serial interface for the keyboard, and of course there's chips to control and drive all that as well, right? As well as, of course, the video, which is up here somewhere, the video processor, okay? All right, what else do we got here? Interrupt logic. So it tells you that the Z80, they want to run their Z80 in mode 2. I mean, this is an enormous value, having this information, because this is the intent. They designed it so that it was supposed to be used this way. We don't have to ask the question, what interrupt mode is it supposed to do? How does the vectors get over there, and all that other fun stuff. They come right out and tell us they run it in mode 2. Therefore, when we look at the schematic, we'll see the handshaking logic that is used to send the vector information over after an interrupt, okay? And they tell you flat out, here's the the decreasing priority, the interrupt levels. If they all interrupt at once, who has highest priority? And that's the serial received from the cable. The next one is the sender, keyboard, and so on. And they hook up their video frame synchronization output to one of their interrupts, so we can get an interrupt per field or frame. Reset switch, obviously. There's a control register that lets you diddle around with those LEDs, turn on and off the ROM, control the RF switch, whether you're supposed to be sending the video from the NABU or going to bypass and watch regular TV on your set, as well as control the printer. Status byte is used to read what's going on, and that's hooked up to all kinds bits of input and stuff like that around the board. Like, you can ask what device is interrupting and stuff like that. So it gives you the address numbers. These are the IO port addresses for all the stuff. It tells you in the control register, if I'm going to write a value out, which bits are used for what. I mean, this is beautiful, right? I mean, we have the schematic, you can figure it out, but we have the schematic, which is the truth, and we have this document, which tells us the intent, which is always a godsend. When combined with the truth, you now have a true understanding of what's going on, how to write to the printer, how to make sounds. What else is going on here? Which ports are used for the VDP, so we don't even have to reverse engineer any of this. We can just sit down with this. This is how to write your own boot ROM if you want to. What pins are used for what parts of the signals on the printer, or the phono, the video out, audio out. We know the video works because we just saw that come out, even though the colors are probably out of whack. The HCCA. So this is their connector that talks to their set-top box. And I am a little bit surprised. They got transmit plus and minus, receive plus and minus. There is no ground. Now you might argue, well, it's differential, who cares? Well, you do. Unless it's galvanically isolated, and I don't think this is. You have to have a common ground, or it's still a bit of a loss. I wonder if the DIN cable has a metal outside shield around it that is probably grounded. I'll bet it is. And besides, if you're going to plug this into your set-top box, your cable set-top box, the ground shield on the cable, the coax that you saw me pull out of the box, would also create a ground. But I'm surprised they don't explicitly talk about a common ground in here. Anyway, so here we have the keyboard, which is going to be differential as well. And there's going to be your, see here it says shield ground, but this one doesn't say. I'll bet it is. Why spend all the money to make it isolated, That does cost a little more. And these are probably super cost sensitive environment here. So, okay, what do we got? The LED 8-pin inline. So this is the ribbon cable that I looked at earlier, that white ribbon cable that reaches up to the front panel, plugs into the motherboard. What else we got? Option cards. Which pins are used for the data lines? Here's this chip select. Well, card 1, card 2, card 3, they all have different ones. This is the IO port address we saw earlier. They throw a couple address lines. You don't need all 16. There's the read and write signal. It looks like they're active true, which seems odd to me. I'll bet this is just poorly documented. You can see it in the manual and the schematic later on. I suspect these are supposed to have a bar over it. As may this, the weight, and so on. They have an interrupt acknowledge that comes back as well. That's interesting. We should see how that works, because that's not just right off the Z80. I think these other ones are. It's got a reset and an audio. And this is kind of neat. You can plug in a card, and each one of the cards can contribute. You'll see they have a summing amplifier on the motherboard. Some of what that stuff is in there. Sums up the audio from all these separate boards, so you can actually add more sound if you want to. Do not exceed 5 volts. Important safety tip. System clock, as I said before. Surprise! There's your color burst frequency. So they got one crystal. Why buy more? So they just run the whole thing off of this. I get a little miffed when I waste the opportunity to run all the way up at 4 megahertz. But, you know, every dollar counts. And back in those days, these were probably not exactly free. It's not like one 5-cent chip, if that. You got board real estate, sockets, more stuff. It's using more power and everything else. This also goes through a divide by 2 circuit to generate half the frequency. And this is used to run the bit rate clock on the HCCA UART when it's running in 16x mode. I talked about this a lot with the Z80 Retro, and we're connecting up the serial I/O device. The clocks run, very common to run 16 to 1 faster than the bit rate. You divide this by 16 and you get, surprise, 111K. So this screwball frequency here from the color burst frequency is why it runs at a weird speed. Okay. And, again, if they're going to buy 1,000 of these units, or tens of thousands of them for a cable system across, a bunch of communities, those costs add up. So, I'm not going to diss them for that, but at the same time, I'm going to diss them for that, because now we have to deal with this screwy clock speed if we want to build a circuit that plugs directly in without, adjusting and hacking up the circuitry that's in the NABU. So what else we got? Power and ground, plus or minus 12. Back in those days, you used to get all this sort of voltages because a lot of chips needed the plus and minus 12. Memory chips especially needed that. All right, so what else do we got? This is a suitable voltage for me. 60 hertz, less than an amp, with a 30 amp peak half cycle. When you first turn it on, it temporarily can surge that much. I'm not used to seeing this rating on a lot of power supplies and consumer goods. That not in my face. Maybe that's a Canadian thing. 40 watts, blah, 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 ripple current, yada, yada. So this is not exactly a user manual for the machine, right? This is clearly the technical manual for people developing boards in hacking, if you want to. What else we got? Keyboard. Here's your 6801. It's got 2K of RAM, a whopping 128 bytes of RAM. Try to buy that small of a RAM chip today. Oh my gosh. Okay, a bunch of parallel I/O lines. Timer. Full duplex serial interface, yet only one direction is used. And it runs on the enhanced 6800. Now, when I was in college, one of our electronics labs was based on the 6800. So I'm pretty familiar with that. Although it would be reaching, a good couple of decades ago, like 1982. But yes, I remember that chip. This is the predecessor. The 6502 was kind of like this thing costs too much money kind of attitude. You Google it and see what happened back in those days. And when they designed the 6502, they wanted it to come out at a lower price, because these were like a couple of $100 a piece, if I memory serves. And this was like, in the mid 70s when everything cost a lot of money. So the 6502 coming out south of $100 a piece was awesome. And it's what went into the Apple One, Apple IIs, or a 6502 base. And that's why you didn't have the 6800. And I think I read somewhere that Jobs went and tried to negotiate a price on the 6800, couldn't get it, and said, okay, forget it, we'll go to 6502. Joysticks, they talk about filtering because of static discharge, a huge problem. If you're going to take a piece of wire, now remember, this is 1984, 1990, you got a long wire. And TVs had tubes. They had cathode ray tubes. And anybody who was around back then, it took a piece of wire and gently draped it across one of those screens while holding one end in your hand. Holy Mother of God. You can get quite a static discharge in there. So if you had, your joystick cables and you're playing around and you kind of fling it and it drapes across your TV screen, you're discharging a lot of static into that cable. So yeah, this is read and heed if you have a CRT, and nobody does today. So this is not a problem anymore. But at the time, this is a big deal. They also note RF radiation coming out of the cables the other way. If the CPU happens to be chattering in those wires, which it does not do, especially from the Atari style joysticks, although you can get some back noise on those lines. Point is that the Atari joysticks were passive contact closure kind of design, and with pull-up resistors usually inside the receiving end, which would be the keyboard, right? So there shouldn't be noise going out there. But, there can be if you don't put some capacitors or maybe some ferrite beads or something on those signals to squelch out power supply ripple noise and stuff like that, which definitely could be a problem. And I've been told that when you go for your FCC rating, you design a board, a lot of people end up failing because the RF comes out of their power cords. And the easiest way to get rid of that is to throw ferrite beads on the power, on the lines that go out to that cable. That's a thing. Software, here we go. Reads a byte-wide read-only register to obtain data from the keyboard. All right. HCC. I guess that HCC is the thing that I have. The HCC-A is the HCC adapter, which is the cable box, okay? Which is why it said HCC adapter not found, or adapter not found. Okay. Keyboard does this. We've seen this before. Game controller. These are your Atari style. I recognize that. And it says here's how this thing squawks, which is fine. These are the bytes you're going to get. And this is nice to know, so we don't have to reverse engineer the ROM inside the keyboard to figure out how the data comes out of that cable. That's very nice of them. I'm very glad to see this, as well as the joystick data that comes back from the joysticks here, blah, blah, blah. You got an 80 or an 81. I think that what happens here is it sends this byte followed by a second byte that represents the data of the joystick buttons, because the keyboard would only normally generate values from 0 to 7F, I think. And the byte that comes after the 80 or the 81 is, I guess, this. 101, and then we got fire, up, down, left, right. And that's right, the Atari joysticks only had 4 directions and one button. So that's all you would have had. It's a fertile. In here it talks about the encoding and what all the keys do, and here's all the key map. And they do have extra numbers in here, so that's interesting. What's it say about 80 and 81? It says JS1, JS2. So Yeah, I don't know. I'll have to read it a little bit more, but glancing through here, it looks like we can just plug it in and get bytes out. This looks like ASCII. Yes, it is. So it's set up in the that I would argue is the obvious way, and some extra fancy keys generate other signals. The your TV control buttons and stuff. Some of the function buttons on the keyboard send funky extra things like right and left. Obviously, that's like play and pause. Maybe is the Canadian version of the not quite international symbol for play and pause. And what else do they got? They got a yes and a no button and some stuff like that on there. Okay. I don't know. This is what then shift, right and left, up, down. Oh, if you read the text in here, because I gave this a once over before recording, these extra function keys will tell you when the key is pressed down and send you another code when you release it and it comes back up, which is a lot like you see on IBM PC keyboards. Also give you a down and an up separate. Now, of course, the IBM PC keyboard gives you an up and a down for every key. This one only does it on the function keys, the regular letters. You're subject to regular, the key has been pressed. And if there's auto repeat, which I'm sure there is, you'll get this over and over again. It won't simply say it's been pressed down and released now. Here's your memory map. It's pretty simple. You got 64K. If you turn on the ROM, it'll map in and cover up the RAM down here. And they did exactly what I did with the retro board. If you look closely at the schematic and read a little bit of the text, the ROM, when it's turned on, is the thing that the CPU will read if you access the byte range that the ROM is in. And if the CPU ever writes to the same byte range, the ROM will be turned off and the writing will go into the RAM. So we can play the same exact game if we want to, where the ROM can copy itself into the RAM at the same exact address in the RAM that it appears at in the ROM. And when it's done copying, it can turn the ROM off. Now, unlike the retro board, this is the real deal. And back in those days, ROMs were slow. So some of the extra chips on the motherboard are wait state generators. When you execute code out of the ROM, it runs slower than if you execute code out of the RAM. So I don't doubt for 1 minute that the goal here is to get rid of the ROM as quickly as possible and to just ignore it and not care to bring it back again, which is the way I did it on the retro. For systems that work this way, that was kind of how they would work anyway. The fact that they can bring it back in again is nice. I couldn't do that with the retro. I couldn't figure out how to do it with the retro without adding more chips. So given the real estate that I had to work with and the constraints that I decided to put upon myself, I didn't have the ability to put it back on again after I shut it off. So down here, this is kind of a weird way to show this. It does beg a question. Are these bytes that appear in the memory, or are these I/O addresses that appear in what I would consider to be a completely separate address space? And if you look at the schematic, this really is the I/O address space. Whoever drew it in here in this, I'm like, okay, fine. I mean, in a way, it's all right because you use the same address bus and the same data bus to perform I/O operations. But this is the first and only time I've ever seen anyone talk about their I/O ports and their address ranges by showing where they appear in your memory map over here. When you're dealing with a Z80, well, I'm usually very much more accustomed to here's your memory addresses and what they're for, and a completely separate drawing for the I/O addresses. So this one threw me for a twist when I first saw it. They give you all the port numbers for all the parts, the video processor, the printer, keyboard. Again, beautiful. We don't have to reverse engineer the EEPROM. Here's all the chip numbers and their markings on the schematic, and what power it uses. Okay, great. You can put a 4K or an 8K EEPROM in there in U53. And depending on the chip, the power comes in on different pin numbers. All right. So you got to keep that in mind if you're probing around. It turns out that pin 12 is pin 14 because these have different packages. The 64 has 4 more pins in it. So pin 12 is the lower, the end pin on the first row in a whatever, a 24 pin package. And pin 14 is the last pin on the first row of a 28 pin package. Okay. So it makes sense in that the wires are permanently connected and you can just pop out a chip and slap the other one in. They're pin compatible, in other words. Okay. So they give you the usual culprits in here, and you can recognize a few of these. The 373, they use the same latch that I use. 8-bit latch for probably an output type of thing. A 241 is what is that thing? A 240 is an inverting 8-bit buffer. A 241, I believe, is a non-inverting 8-bit buffer. 3900 will be some sort of an op amp. That's probably their audio summing amplifier. Here's your 74LS138. This is the same thing I use. That's going to be their memory or their I/O port decoder or something. I'm sure of that. There's their video card. 7474. These are like flip-flops, single bit latches. So this is probably used to divide the clock by 2, for example, and other such things. All right. Photo of the board in here again. And a schematic. And if you zip through here, you see a lot of the usual culprits. This is your dynamic RAM, and they abbreviated it. This represents 8 single chips, your CAS, RAS, and some gates to cause signal delays and stuff like that, and some timing logic so that the row and the column come in at different times. And since it booted up and it ran its own self-test, I'm guessing the RAM is probably fine. The CPU is running. All these gates are basically going. You can start to see stuff that we would expect to find. The ROM select signal. This is going to come from the latch. And this is the thing you can turn on and off. This is your EEPROM right here. And it goes into some gates and stuff like that. So the chip is enabled if this is low, which is if this is high, which happens if that's a NOR gate. So if any of these are 1, this is 0. So if all these are 0, then the ROM will be enabled because this will be high inverted to a low, and that enables it up here. When that's enabled, this messes around with something here that's also connected to refresh, which suggests that it has something to do with tinkering with the RAM. So maybe the RAM is refreshing. I don't know. Not a major thing. You can see write and read of bars here. I suspect that what we saw earlier should have had bars on them in the summary listings of the signals that are connected to the I/O expando connectors, which are actually in a drawing down here. We can look more closely, and absolutely, these are those connectors, and your writing and your reading and your weight. These all have bars over them. These are your 241s. I'm not used to seeing them drawn this way. I find this a little annoying. I like to see the little triangular buffers in there. It's got these pins paired off because it's not a simple, 8 buffers all going one way or the other way. It turns out there's one facing to the right, one facing to the left, and so on. And you can enable either direction A or direction B. So this is, again, old school. All right. So there's 8 buffers here, but you turn on 4 output drivers at any one time, or you turn on the 4 input drivers at any one time. So that's what these 2 signals are all about. And this handles 4 bits in here, and the other 4 are there. Today, you'd use a 245 or something like that, and just do all 8 in all one chip with bidirectional control and everything else all in one package. However, having said all that, a 241 is an enormous drive current that you don't get out of a 245. So, I mean, we're talking like 40 milliamps of drive. I ballpark 20 to 40 milliamps, which is just enormous for a simple buffer. Okay, so these are buffer drivers, right? A 245 is just a buffer, not a high-end driver like that. So these are better if you need that extra current, and maybe they do. I don't know. And here's your read, your write, IO request. I don't know what this thing is. U30. This is another OEA, OEB. This is hardwired to always be on. And this is all aid, probably, yeah, you can see arrowheads over here. Again, I would wish they would put the triangle so we can see which way the thing is going. But these are the signals from the CPU. Go through the driver so it's isolated, unlike the retro board. And I just haphazardly connect the CPU lines directly to that connector, which is okay-ish, as long as you don't hook up so much stuff. This thing, these are the same chips that are in like S100 boards. You could have 20 slots over here and wouldn't have a problem. On a foot-long set of bus connectors like you see in a MSI 8080, and this will handle it and it'll work fine. Although not very well over 4 megahertz. Maybe 8 megahertz would work. I've never tried it. You know what? I take that back. I built a National Semiconductor 32000 system, which I think runs at 10 megahertz, and stuck it in an S100 cage, and it worked. And the memory was plugged in a separate card over the bus and everything else. So maybe you can get a little more speed in there. Although I wouldn't, bet my life on it. It's also possible, since I built it in 1985, that I've forgotten the clock speed and maybe it runs at 4 and I forgot. I don't know. Anyway, these are really great heavy duty drivers. This over here, the Zener and some other, 100 microphone. This must be this is a power supply connector. I have no doubt about that. It would be nice if they labeled it. It's a Canadian schematic. It's the way they do things there. Eh? In fact, I got a Canadian viewer I know. I was talking to him the other day. Is this a thing in Canada? Where you abstract a lot more away than you might see me try to do with KiCad? Is that a thing? Or maybe it was just the 80s, Who knows? Here's your sound chip. Come on, what do we got? Here's the good stuff. So here's the video controller. And this is actually why I bought this thing. I wanted to see somebody else do what I'm thinking about doing. Maybe there's probably hundreds of thousands of dollars of research that went into this design. And, let's have a look-see. Look what they did down here. And when I have the video coming out of my chip and I built myself the emitter follower, I mean, that's not a big deal. Everyone seems to be doing that. They have a couple of jacks. You look at the motherboard. These are not populated. This is the one that comes out of the back that I just plugged into my capture device and used, that we saw with the wonky color on it. So what else is going on? You got another transistor over here that goes to Vimdo. Whatever that's doing, I don't know. The base of this thing is connected up to the video that comes out of this chip. And the base of this transistor is also connected to the video that comes out of the chip. This is a scan of a, paper, I'm sure. It's kind of hard to read. You can see the dot here, a dot there. There's no dot here, and that makes sense. There wouldn't be one, because why would you ever connect the base to the emitter of a 3904? It doesn't really make sense. So they have a 39 ohm resistor between ComVid and this transistor, which I did not put in my design. I don't have a place to put such a thing. We can hack one in if we want. It's not like their color's great. Mine looked a lot nicer than theirs. I'm just saying, even off the breadboard. So they go through an emitter follower. They bring it to ground in a 180, and then they squawk it out this way. The Steve Ciarcia design had they have like a 39 And I think it had a 330 ohm over here, but it's a similar kind of a design. Steve didn't do this. He put some over here. So this is actually going to be a divider off of here anyway, because I'm sure, yes, there's another resistor over here. So they have a divider, roughly similar to the one that Steve used. They did it before the input to the transistor. Steve put the divider on the output of the transistor. Roughly the same division. This one has an added 390 puff capacitor over here. I did not design this in. I did not think of this. And I've never seen this in any other schematics that I've Googled around, saw floating around the internet. This may be useful. This 390 puff on the video is going to cause the high-end frequencies to be rolled off and blocked and shorted out quite literally by this little teeny capacitor. And when I looked at my video on my oscilloscope and zoomed in a little bit, I saw some high frequency noise in the color burst signal and stuff like that. I gotta wonder if they must have seen the same thing. This is probably here to filter out the digital switching noise of all the circuits here chattering like crazy that can cause noise to get in on this signal. I bet that's what this is doing here, all right? I'm not sure what the heck this does. This signal over here, Mr. Vimdo, goes over to the RF modulator. So this is another amplifier. It's another emitter follower. That is obviously tuned with some sort of voltage division to get the amplitude right to go in their RF modulator. On the Z80 Retro, I wouldn't have any of these parts because I'm not messing with that here. I did this on my design. Here's their 5-volt power. Remember the extra 2 capacitors I put on there, and they have a coil. I marked it as 10 ohms. I was talking whether we might put a coil, could be a ferrite bead or something like that in here. This is exactly what they did. Some sort of an inductor with some, this is a half of a pi filter is what they're really doing here to create a nice clean 5 volts, try to get rid of any switching noise that could sneak in here before it goes through their amplifier. And even if it does, or comes out of the video chip itself, they're going to get rid of that over there, snub that sucker out. If you look closely in here, they do the same thing again. This did not occur to me. I'm like, oh, I should have done this. And the way my board is laid out, this is not easy at all to add because I have the inside power planes in there. What they did is they put an inductor here, another half a pi on their video chip itself. I just put a giant capacitor, relatively speaking, so did they, right across the VCC and ground, the power. They have a local, bulk capacitance over here in their, on their power supply input. And this inductor will be a good idea. I think it's a better idea here even than it is over there. Like I said, I'm not convinced that this is going to make a big difference, but they were so cheap they didn't even want to buy a second crystal, and yet they put this in here. And that's 100 microfarads. That's one of those axial capacitors that we saw on the motherboard here, all right? So they paid money to have this thing soldered in. I'm sure it's cheaper than a crystal, but still, they felt the need to do this. So, and like I said, it's nice to see this because I'll bet they tested it a lot better than I did. So that would be nice. And God darn it, my next revision, I'll probably do this here as well because I'm sure that'll clean it up even more than what I've got. And this here is probably the thing that divides up. Yeah, there you go. So this here is the clock output. You have the crystal that runs at the color burst frequency, right? Then the chip comes out with a reference square wave. And then they run it. What the heck is this thing? This suggests that this clock is not exactly square. Maybe they want to clean it up a little bit and then run it through a gate. This should change the duty cycle a little bit, I think. Anybody? comments. Yeah, this was probably an experiment to figure out what this was that they needed to do here. And because the Z80 wants a relatively close to 50-50 duty cycle, they probably had to do this because this clock, I'll bet, is like narrow and in the high and long in the low. It's, it's not 50% high and 50% low. It's probably a narrow spike that goes up with a long low, or the opposite. It could be high a long time with a little glitch down and then back up again. And maybe this thing widens it out and makes it more even. And then it's not uncommon to see you go through a gate. I don't think anyone cares that this clock was inverted. I'm sure it just runs through an inverter just to have gone through a gate to make sure that it has a nice driver here. And sometimes you'll see a couple of these in series in order to just make sure that you've gotten yourself away from the more analog-ish signal that might be coming out of an oscillator with rounded off edges or slow slew rates and things like that, just to clean it up a little bit and to drive it before it goes into a digital thing. This one down here, I'm sure, is doing the same thing, and it goes into this flip-flop. The clock here, every time the clock ticks, Q bar is loaded back into the data. So this divides the frequency in half, and they take that, and you got a 179, and this is your 358. These are the main clocks that run the whole system, all right? And what's this thing? This is the serial controller for the thing that talks to the cable company, right here. These are your RS422. That's what those drivers look like, with a 180 ohm terminator for the receiver, and here's the driver that goes out. Put a couple of 1.1 microfarads in here, and these will be snubbing out glitches and stuff like that. Since they don't have a ground, they may have a problem with such things. I'm surprised that they don't have a shared ground on this connector. What's U12 and 13? I think that's the last page of the schematic, yeah. Then you got a picture of a guy that looks like he's right out of the 70s here. Disco Stew from The Simpsons right there, right? And there's the family, the loving family, a loving Canadian family that cannot help but take their NABU keyboard and show that you don't need to have the keyboard on the screen. You can take it with you up to 8 feet away, or however long that cable is. Yeah, you gotta love these historical images. What does it say? Computer magic comes home to television. The NABU network. What else? Here's your Qbert game, and they got a little block diagram. Well, there you go. Here's your cable that comes into your house. Head-end computer. And this is the regular video cable TV head-end. And then you combine. What are you doing? You're taking the computer. This is going to be, get a new art department, because this is a bidirectional cable, because this is definitely going to send data back up here. Boy, it's possible that it doesn't actually send data back up this way. Wow. That's creative. If it is a one-way communication system, then that would, if it really is only one way, then what would happen is that periodically this machine just keeps resending out anything that this box might ever need. Oh, by the way, if anybody wants to play Qbert, here's the code for Qbert. And then a little while later, by the way, if anybody wants to boot up CP/M, here's a copy of the operating system. By the way, if anybody wants to play Pac-Man, here's the game. And go into a loop and just continuously send that out. Wow. It just dawned on me. I mean, that's a really simple way to do it, but it means you got to wait until the next time it comes around. And if it's only going around at 111 kbits a second, you might wait a little while. I think that this is just drawn poorly. I'd be surprised if they don't have a system that says, "Hi, I want something," and it allows it to talk into the cable and let this thing come back out. I'm sure somebody can correct me if I'm wrong. But in 1984, I did work a little bit with people that run cable systems, and they did have back channels even back in those days, but they were very low speed, and they didn't always work. I met somebody that ran a cable company, a cable system in an apartment building in Chicago, and they said it never works. It was a piece of crap in the 80s, that it never worked. So it's possible that this is a one-way communication system, which makes me think that if we did rig up a little adapter that talked to RS-422, which would come into the NABU right here, that's this thing. Well, actually, I don't know if it's this one or this one, but given the, high level of abstraction in this drawing, it doesn't matter. It would connect up either way. That comes in right here. The fact that this is able to send something means that it could actually be talking to this adapter, the HCA up here, or it could actually go through here and go all the way out onto the cable network. I suspect it goes all the way out on the cable network. I wouldn't pay all this money to build this system and not provide a way for someone to be able to buy something. All right. And that would require you to be able to send a message up here saying, I want something, and I'm me, and I'm doing this, and please bill me. Right. So I suspect that this is the not exactly the best choice of an icon right there, or an object in this diagram. All right. So they left it out in the rain. Yeah, I wonder when this was shot. Maybe this is the, when the project did its run, and these were the leftover ones, and whoever, maybe somebody bought all this and shot this picture when they delivered them to their backyard. And then are now selling them on eBay. Hurry up and buy them before winter comes. They may not make it through the snowing season. And there it is. All right, so next time, who knows? Maybe we'll try and put some code in here by replacing this boot ROM with another chip, or I have another option. This is in a socket, as is this, as is a lot of the expensive big chips are socketed. That's very nice of them. So if I ever decide to get rid of this and it's no fun, I can just take the chips out and put them something else. What else can we do? We can remove the Z80, and I can plug in an in-circuit emulator. So tune in next time when I do just that very thing, and maybe we will have a look-see at what's in this ROM, and maybe we'll reset it and boot it up and manually enter some commands to say, set IO port number, 27 to be value X, and IO port number whatever to some other value, and actually ask the sound chip to make a sound, or ask the video chip, like you saw me playing around with on my breadboard. We can do the same thing with this. Initialize thyself, set the background color to this, and so on, relatively easily. And if we can do things like that, we can then actually use the in-circuit emulator that I happen to have. We can actually turn off the ROM and upload a bunch of data into these RAM chips, which must be these or these. One of these rows of chips are going to be the RAMs. They're all going to be the same. These are all different. These are all the same. These are the RAMs, right? Actually, yeah, these will be your data RAMs. Boy, where's the video? You know what? I'll bet these are the video RAMs that go with this chip here, because I don't see any other ones. These would be the data. Wow. I don't know. We'll have to look more closely. This photo is, I can't read the chip numbers in here, but these are MC chips, Motorola, and this looks like a different one. So, yeah, I don't know. I'd expect to see 8 chips all be the same for the 64K RAM, 8 chips all the same for the 16K of RAM, which I assume they have the full 16K to go along with this and so on. Anyway, the point is this one's all hooked up. It's all powered up. It's tested. We've seen it work. So if I stick the in-circuit emulator in here, I can diddle around with this, and maybe we can push some code into the RAM and see if we can wake up parts of this board. That'll be kind of cool. All right, so thanks for watching. See you next time.